All right, problem 4 says to find the volume of the region bounded above by the sphere x squared plus y squared plus z squared equals 4, and below by the cone z is equal to the square root of x squared plus y squared. Okay, so here is a picture of our sphere. It's just the sphere centered at the origin of radius 2, and here's our cone. And we want the region bounded above by the sphere and below by the cone. So in other words, we're looking for this region bounded by sphere and cone, right? The stuff in between. And so, in fact, we're finding the volume of this ice cream cone region, right? So we get this cone here, and then we get this little spherical cap on top. And this red curve here I've just drawn, that's going to be just the curve of intersection between the cone and the sphere. Okay, so now to set up an integral for this, there's a few things we need to sort out. Okay, the first thing is what's the integrand? What's the thing we're actually going to integrate? And for that, well, we want to think about approximating pillars here. So if I was to say, fill out our region with a bunch of these pillars that run from cone up to sphere, right? We're going to compute the volume by just stacking, right, a whole bunch of these pillars as we run through the region and then adding them up, and that's what the integral is going to do. So what is an expression then for the height of one of these pillars? So let's do that over here. So for the height, well, it's just going to equal the z height on our sphere minus the z height on the cone. Okay, and so that's going to equal what? Well, the z sphere, right, we have the equation of the sphere here, and since we're looking at a portion of the top half there, we'll take the positive root of 4 minus x squared minus y squared. And then we're subtracting from that z cone, which is just the square root of x squared plus y squared. All right, so this is going to be our integrand, right? And again, this is really analogous to what you do in Calc 2, thinking about the area bounded by two curves, right? We're really just doing here top surface minus bottom surface. Okay, what now is the domain of integration? Okay, well, if you imagine, say, smushing your ice cream cone down onto the ground, so onto the xy plane, we're asking what region down here are you going to cover? And if you think about that, well, if I just take this curve of intersection here in red and project it onto the xy plane, okay, I, in fact, am going to be describing a disk. Okay, so I'm smushing my ice cream down, splat, right onto the xy plane, and this region in red, this circular disk here, will be our domain of integration. Now, how do I know the radius of this boundary circle? Well, to find that, we can just set the z coordinates of the sphere and the cone equal to one another and do a little moving around, and you get this relationship. X squared plus y squared is equal to 2. So in other words, that boundary circle for the cone and sphere has radius root 2. Okay, so now we're in a place where we can go ahead and set up an integral for our volume. So the volume here, this is going to be the double integral over this region D of our height function, right? The heights of these various pillars that we're stacking up here to fill out our region. All right, and now we got to compute this thing. And looking at this integral, well, the integrals in terms of just x and y are fairly messy, and especially with square roots and you have squares in there, typically you want to be thinking something like maybe trig substitution, which I really would like to avoid. Okay, now polar, on the other hand, seems pretty appealing for two reasons. One, the region of integration in polar is really simple. So in polar coordinates here, r goes from just 0 to the square root of 2, and theta goes from 0 to 2 pi, so that's really nice. And the other thing that's appealing here is that the integrand has a bunch of x squared plus y squareds, and we know that that is just simply r squared. So polar is going to be the way to go here. So let's do it. So here we're going to get the integral, and I'll do it as a dr d theta integral. So it'd be 0 to 2 pi for the outer limits. Those are the theta limits. And then 0 to the root of 2 for the r limits. And then we're looking at the root of, and this is 4 minus the quantity x squared plus y squared. So that'd just be 4 minus r squared. And then here, notice the root of x squared plus y squared, that's just going to be r, which is nice. And then for our dA, don't forget that factor of r, we have r and then our dr d theta. All right, this is really, really nice. So what I'm going to do now is distribute that r, and now we're having to compute r times the root of 4 minus r squared, and then minus r squared. Okay. The other thing to notice is that our integrand does not depend on theta, right? We keep seeing this pop up. And so as a simplifying step here, we know, right, that this inside integral here, the r integral, that's constant when it comes to theta, so it can come out front, and then we're just going to integrate theta from 0 to 2 pi, and so in fact we're just going to get a multiplier of 2 pi. So I'm just going to say this is 2 pi times our r integral. So that's a nice simplifying step. Okay, and now the next thing is, how do we go about computing this r integral? Well, for this first piece, okay, we can compute this using a substitution, because if we just notice, the derivative of 4 minus r squared is minus 2r, and we have this factor of r right out there, right? I can say, well, let u equal 4 minus r squared, and so du would be minus 2r dr, so that's going to handle this first piece, and then the second piece is not bad at all. It's just integrating r squared, and that's just going to be r cubed over 3. Okay, so let's do it. So we're going to have 2 pi, and then I'll put parentheses here, and I'm going to handle this first integral with the substitution, and let's change the limits of integration as well. And so notice when r is 0, u would be 4, and when r is the square root of 2, I'd get 4 minus the square of root 2, so it'd be 4 minus 2, which would be 2. And then I'm going to have an r dr, and from this, r dr would be the same thing as minus du over 2. And then I have this square root term, which is just going to be the square root of u. All right, and then I'll now apply that r integral to r squared, and that's going to give us an r cubed over 3, and here the bounds are just in terms of r, so that'd be from 0 to the square root of 2. Okay, so we're getting there now. We got, for this, just the integral of the root of u, which is 2/3 u to the 3/2, and the 2 from the 2/3 will cancel with this 2 here, and so I'll get 1/3 and then u to the 3/2, and notice I didn't write in the negative. For the negative there, I'm going to use that to switch the bounds of integration, so the bounds now would be from 2 to 4. All right, and then minus, plugging in the root 2 here, root 2 cubed, well, that's going to be 2 to the 3/2. That's one way to write it, but you could also write it as 2 root 2. and then that's over 3. Plugging in 0 would just give us 0, so we would get that. All right, so we're getting there. We got now plugging in 4. We're going to get 4 to the 3/2 power, and the 2 here, the denominator, is a radical, so we're taking the root of 4, which is 2, and then we're cubing it, so I'm going to get an 8. Here, I'll just write this as 8/3 here. And then we have minus what we get when we plug in 2, and that's going to be 2 to the 3/2. And so that's what? Root 2 cubed. Oh, and that's the same thing here. It's 2 root 2 over 3. And then I still have my minus 2 root 2 over 3. And now we can go ahead and just combine all that. So we have 2 pi times, and then we have 8 minus 4 root 2 all over 3. And I'll go ahead and factor out that 4. So when all is said and done, I'm going to get 8 pi times the quantity 2 minus root 2 all over 3. All right, so there would be the volume of our ice cream cone, and that's going to do it for this problem. Thank you.